Okay, so let me start on the slides. This is an introduction to quantum computing. And the goals, I just want to give you a flavor for quantum computation and a historical perspective, and emphasize the similarity with classical computing. So welcome to the quantum world. And quantum mechanics developed at the start of the 1900s, and it explains and predicts natural phenomena at the particle level. If you don't have intuition, it's because you didn't play with particles as a toddler. So it's normal to not have an intuition for this. Polynomial time, quantum mechanical processes were taking exponential time to simulate on a classical computer. Well, turning this around, maybe quantum mechanical systems, if cleverly designed, could they solve problems, math problems, with better asymptotics than a normal Turing machine computer? So this led to the notion of quantum computation, started by Feynman and Deutsch in the 1970s and 1980s. So here's a quote from 1975. The quantum mechanical computation of one molecule of methane requires 10 to the 42 grid points, and assuming at each point we have to perform only 10 elementary operations, and the computation is performed at the extremely low temperature, we would still have to use all the energy produced on Earth during the last century. So that's the problem of quantum simulation. The idea is, can we turn this around and use the actual quantum mechanics principles, a quantum computer, to solve a math problem, a hard math problem? So quantum computation, what are zeros and ones? Well, quantum particles with known polarization, spin, etc., can play the role of zeros and ones. And quantum operations simulate Turing machine operations like XOR, and, or not, with a few caveats, many of which we'll sweep under the rug. Classical computer, you have n bits, can take 2 to the n values. On a quantum computer, n bits kind of form a 2 to the n dimensional space. This is the notion of superposition. Everything is possible. So large state space leads to massive parallelism. For example, when you compute f of x on a Turing machine, you're just doing one value. You put in x and you compute x to the n or something. But on a quantum computer, you can actually compute all f of x simultaneously for every x. So, and then another big difference, the quantum Fourier transform, it runs in polynomial time, whereas classically you need exponential time. So Shor's algorithm is based on this. By computing all pairs x, f of x, and then applying the quantum Fourier transform, you learn the period of f of x in polynomial time. In 1994, Peter Shor found a way to factor n by finding the period of g to the x mod n. And you know RSA. What's the period of g to the x? It divides phi of n. So if you get to find phi of n, you can factor. So that's the idea. So Shor's algorithm would solve factoring and also discrete log in polynomial time if we had a quantum computer. And it would break most public key cryptography. So this gives the impetus for the development of quantum resistant cryptography, which you've been hearing about all week long in Kristen's part of the course. So I love this poem, Jennifer and Peter Shor. Okay. If computers that you build are quantum, then spies everywhere will want them. Our codes will all fail, and they'll read our email till we get crypto that's quantum and daunt them. That's a good one. Okay. And let's do a Google search. Well, at least you're scratching your head a little, doesn't it? All right. So Shor's algorithm has several steps for factoring an n-bit integer. First thing you do is create a superposition of all possible x's. Then you compare all pairs x g to the x mod n. And then you use the quantum Fourier transform to find the period. And once you do that, you factor. So this range has to be large enough that you'll go through several periods. If you only had x between 0 and 2 to the n, you'd only see one period and you wouldn't even notice a pattern. So that's why it has to go through larger range. So bits versus qubits, similarities, differences. The n-bit classical register consists of n, you know what, I was thinking about n what? Circuits, maybe? And the zeros and ones are represented by on and off, maybe? I'm sure there are more ways to do that, but if you think about it, like, I don't know. And then what about an n-bit quantum register? I know even less. Might consist of what? N-trapped ions. Zeros and ones are represented by spin left versus spin right. So that's one difference, the physical representation. The second is error correction. Classical error correction is handled with error correction code at a small additional cost. Quantum is much more difficult, and it is a great cost. So it probably multiplies the size of the machine by a large factor. And this talk, we will ignore error correction and pretend all qubits are perfect. So, all right, so in classical versus quantum integers. So an n-bit classical register holds an n-bit integer in binary, like 11001. And how about an n-bit quantum register? Well, it holds a C-linear combination of n-bit integers. And we can just abbreviate this as summation alpha I. And this is called a quantum integer, or quantum state, or superposition. Now, it turns out no physics experiment would distinguish a sum from a non-zero multiple, constant multiple of that sum. So we really should model this as a projective space over C of dimension 2 to the n minus 1, modding out by scalars. All right, measurement. These are really different in the real world and the quantum world. So measurement of a bit or a qubit gives two possible values, 0 or 1. And that's where the similarity stops. So measurement of a classical bit is deterministic. Measurement of a quantum bit is probabilistic. And it causes the state to collapse to the part of the superposition that's consistent with the measurement. So you can think of a quantum state as a very good liar. And it has a superposition of possible alibis. Maybe it's in Philadelphia, maybe it's in New York. But if you ask it a question, it will come up with an answer every time. But answers to future questions are always going to be consistent with that one. You will never catch it in a lie. If it says it's in New York at noon, it will never say that it's in Philadelphia at 12:30, because it knows that's impossible. That has no probability of happening. So it will, oh, amazing. That's, all right, so measurement continued. And superposition, suppose, let's say we measure the low qubit, right? So the probability, you may measure a 0, you may measure a 1. The probability is kind of proportional to the weight. If there are lots of even, if the weight favors even numbers, you're more likely to measure something even. And if the weight favors odd, you're more likely to favor odd. So it's specifically, you take the L2 norm, or the sum of squares, and normalize it so that the probabilities sum to 1. And that's the probability you'll measure a 0 or 1. So if a 0 is measured, then the state collapses to everything consistent with the 0 measurement. So now your sum consists only of the even integers, and the odd integers just vanished, and likely if 1 is measured, likewise. So here's an example. If you began with the state ABC, and let's suppose we decide to measure C, well, you can see that most of the weight is on measuring 0. So like measuring 0, you have 1 squared plus 2 squared is 5. Measuring a 1, you only have 1 squared. So after you normalize, you get 5/6 versus 1/6. Okay. Now let's just suppose we happen to measure a 0. So the new state has collapsed. The other thing has gone away. Now let's say we measure B. Well, you definitely get a 0, because remember, they're a good liar. There used to be a 1 there, but not anymore. Okay, so it's going to be consistent with the first result. So the state now remains the same. Now you measure A, and the chances are 4 to get a 1 versus 1 to get a 0, so 4-to-1 ratio, 4/5 versus 1/5. Okay? And here's an exercise. These slides are online on the WAM web page under lecture. And so the 2018 WAM. And so the probability, here's an exercise. Suppose you measure all the qubits in any order, then the probability to measure J is the norm of alpha J as a complex number divided by the sum of the squares. Okay? All right. Any questions so far? Yeah.
So what do you mean by measure 0 or 1? I'm like slightly confused as to how you know which one is going to be 0 and which one is 1. Is it based off like?
So you just you simply measure. Now, like for instance, if it's spin, the measurement might. I'm going to disqualify myself. I don't know physics. But if it's spin, you might put it through a slit, and spin left goes one way, spin right goes the other. And so you just put it and see where it splats on the wall, and it'll go where it wants to go. But with the underlying state will have an effect. So if the underlying state is kind of balanced between the two possibilities, it'll be 50-50. But if it's not balanced between the two possibilities, then more of them would go one direction than the other. Okay, that's an excellent question. Any others? Okay. Gates. So a classical computer has not, XOR, and AND. You can also set a bit to 0 or to 1. Quantum gates are always reversible. Well, not is okay. If you do it twice, you're fine. What about AND? Like 0 and 1 is 0, 1 and 0 is 0. That's not reversible. So quantum gates have to be reversible, and also they act on the whole superposition at once. So let's just see some examples. These are called the semi-classical quantum gates. Not is just you toggle a bit from 0 to 1. The gates are set up physically by the physicists, and I thank them very much for doing that for me. So C naught is B plus gets A, analog of XOR. Toffoli is C plus gets A and B, and it's the analog of AND. Okay? Now these are actually reversible. If you did it twice, you would get back to where you were. If you're adding a 0 or a 1. If you do it a second time, you'll just add it a second time and get back to where you were. So all of these have order 2. And the input qubits must be distinct. For example, A plus gets A is not allowed. That would not be reversible because if A is 0 or 1, the result would be a 0, and that's not reversible. So let's see, toffoli is much more costly than a C0, which is much more costly than a not. So I think in a classical setting, whether you do an AND or an XOR, same difference, it's a tick, but in quantum they're not at all the same magnitude of order, of difficulty. Okay, so semi-classical quantum gates, here's an example. Let's just begin with some state 0, 0, 0 minus 2, 1, 0, 0 plus 1, 1, 1. And apply the NOT gate to B. So you do one gate, but it actually affects everything in the superposition simultaneously. You're only doing one gate. It changes 2 to the n things. Now let's do C plus gets B. So we're going to add the third bit onto the second. Add the second bit onto the third. So it happens to each piece simultaneously. Finally, let's do A plus gets B and C. Let's see, these two have B and C set to 1, so it toggles A for those two terms, leaves the other one alone. So exercise, if we repeat the above commands in the reverse order, we'll get back to where we were. Everything's reversible. Okay? Measurement is not reversible, but quantum gates are reversible. So the hint, each semi-classical quantum gate has order 2 and is equal to its own inverse. Yeah?
In terms of like what this looks like in a computer, I guess I've just never seen one, so I don't really know. Like, are there like particles and the particles are like in the computer and they're being like measured and that's how we're getting these bits? Or is it just like data about particles and probability data of whether it's...
Oh, you'll have to go back through Kristen's slide and see that beautiful picture of...
Yeah, that like...
Yeah, I mean, it's got, you know, they have to cool things to low temperatures for some models, and it's very, very physical because they really are using quantum phenomena. So
measurement is going on like in the actual machine.
yes. Okay. Implementing controlled swap. Here's an example. Controlled swap. If A equal 1, then I want to swap B and C. So for example, here's this example, running example we've had. This has A equal 1, so we're going to swap those two, which didn't do anything, in fact. And this is a 1, so we want to swap those two. And that would be the result. However, well, we want to implement C-swap with only those gates that I said, not C0 and toffoli, which are like not XOR and. Well, the tempting thing to do is let's measure A. If it's a 1, we'll swap the two, and if it's a 0, we won't. But that would collapse the state, so don't do that. Instead, try this. If you did B plus gets C, C plus gets A and B, B plus gets C. Does that do the right thing? Well, let's see. If A is 0, we want to do nothing. Well, if A is 0, this step in the middle doesn't do anything. So we've done B plus gets C twice, and it doesn't do anything. That's good. If A is a 1, we've done B plus gets C, C plus gets B, B plus gets C. And that accomplishes a swap. So that's good. Here's another example. Let's do mod 4 addition. So we want a quantum algorithm which takes two qubit numbers, A and B, they're in superposition, and we just want to add A onto B mod 4. How are we going to do that? Well, this is just my thinking space. So here's my inputs. A and B are my inputs, and I'm hoping to overwrite B with the sum. So what is the sum? Well, the low bit is A0 plus B0. The carry is A0 times B0. And then for this, you'd have to add the sum, A1 plus B1 plus C1. All right, so here's what we do. We have an initial state, which is a superposition with some complex coefficients of A and B, where A and B each have 2 qubits. And the first one, B1 plus gets A naught and B naught. You see that was the carry. So the carry is A naught and B naught. So this does B1 equals B1 plus C1. Now we need also an A1, so we just B1 plus gets A1. And then finally we need B naught to equal A naught plus B naught. So we just do B naught plus get A naught. And we're done. We've done a mod 4 sum. Yeah?
So A is between 0 and 3, then, right?
Yeah.
For it to be reversible? Or
That's right. A is between 0 and 3. B is between 0 and 3. And we're just adding B mod 4.
okay, so we have to return A, comma A plus B mod 4 so that to preserve the reverse?
Yes. And if you did these in the reverse order, you would be subtracting B mod 4.
Okay.
Yep. Yes.
To make sure on notation, the plus with the equal sign after it, it's add the two things on both sides and assign it to the left hand side.
Yes, right. So this means we're going to multiply the bits A naught and B naught and add the result to B1. And this is going to be done simultaneously for every integer in the superposition. Right. Yeah.
Could you actually go back to the last slide,
Mm-hmm.
please? I don't understand how the swap works because, wait, I think there was a place where you showed, you're saying, okay, if A is already true or something, you have B is
Yes, if A is
set to
1,
C, C is set to B, and then B is set to C. Doesn't that, are those like all taking place exactly at the same time?
no, sequential. You first add C onto B mod 2.
Okay.
Then you add B onto C mod 2. Then you add C onto B mod 2. And there, if you want to convince yourself that that works, well, if there's only 4 choices, there's 2 choices for B, 2 choices for C, so you could try all 4 possibilities, and you could see in each case, each choice for B and C, it works. Yeah. All right. Any other questions? All right, Hadamard gate. This one is a little different from the others because the other gates I've introduced always took an integer into another integer. But this one is a little different. You put in a 0, you get 0 plus 1. You put in a 1, you get 0 minus 1. So h squared is actually identity. If you did h twice, you would get 0 plus 1 plus 0 minus 1, which is 2 times 0. But that scalar doesn't matter. So 0 goes to 0, 1 would likewise go to 1. All right. So example, again, if ABC is this state, then applying Hadamard, the 0 goes to, apply Hadamard to A. This 0 becomes a 0 plus 1. So 0 plus 1 with the other 2 bits untouched. In here, the minus 2, 1, 0, 0, minus 2. The 1 goes to 0 minus 1. The other bits are untouched. And for the third one, the 1 goes to a 0 minus 1, and the other bits are untouched. And you can then simplify, and you get some new state. Okay, so that's how Hadamard works. Here's some exercises. If you'd like to go back through the slides, you can try applying the Hadamard a second time and verify you get back to the original, which you should because h squared is 1. And you will pick up a multiple of 2, but this global multiple doesn't actually affect anything because we're modding out by scalars. And then you can also verify another exercise that if you apply Hadamard to A, then you add B onto A, and then apply Hadamard to A again, it actually ends up multiplying by minus 1 to the AB. So it affects the complex numbers out front. And those are exercises for later. Creating a superposition. This is one of the big roles that the Hadamard plays, is that it creates a superposition. So what you do is you start with all zeros, and then you apply Hadamard to each qubit separately. Remember, 0 goes to 0 plus 1. So here we apply it to A, and we kind of got a 0 plus 1 there. Now apply it to B. Well, now we got A is through 0 or 1, and now B also distributes through 0 or 1. So this is sort of like a souped up foil, right? C, you do it to C, and you've now got the sum of all possible integers from 0 to 7. So that's the use of Hadamard. It's notice if this is n long, then to create all possibilities, you need only n gates. It's almost no work to create this superposition. Now we can factor an n-bit integer. You first create a superposition of all the x up to 2 to the 2n. Then you compute all pairs x g to the x mod n. For this step, you'll want to use quantum gates that Toffoli, C naught, and not, and just kind of mimic classical computation to some extent. And then in the last step, use the quantum Fourier transform to find the period of g to the x. Okay? So step 1 is you start with 3 n qubits, all 0, apply h to the first 2 n qubits, and you get, ooh, what is that? Oh, okay, 2 to the 2n power, not 22n. Okay, and then in the second step, you just apply quantum gates to compute g to the x mod n. And here are some references, which I very much recommend. Okay.